Hello, what I want to talk about is beginning to look at some real data. So, we're at a point in the course where we have looked at frequency analysis and we've looked at time domain analysis, and we've talked a little bit, or going to talk a little bit about filtering and the importance of filtering. So, what I want to show you here that I have on the screen is an actual data set. This is a set of EEG data. It was taken when the subject was at rest. What we have over here on the left side of the axis are channel labels. This is a 65 channel EEG, meaning it has electrodes at 65 different locations on the scalp. And so it's basically recording EEG activity from 65 channels. As you can, and these are raw data, so this is imported directly. It's not filtered other than a little bit of hardware and preliminary filtering that's done in the system itself. But when the person doing the analysis of the signal gets the data, it looks like this. And so we'll start paging through, and just first of all, you'll notice that not all 65 channels are present. We just see a limited number of channels. That's because we haven't filtered out any DC offset or done any low pass filtering. Then you'll notice that we see, and by the way, the horizontal axis is time, and in this case it's displaying in seconds. And I'm using some special EEG software that allows me to display this relatively easily. So you can see that here at 8.5 seconds, we have some kind of major movement that goes on, and lots of just junk in the signal. Lots of stuff going on here that is not EEG. I can change the scale here. Maybe you may be able to see more channels. Yeah, there we go. So you can see more channels this way by changing the display scale, or if you want to zoom in on one specific channel to just kind of see, just amplify here what's going on just on the screen. So you can see just a lot of stuff going on here. Pretty messy signal overall. Now I'm going to go in within this software and just do a really quick filter. This is not actually what I'll have you do, but it serves the purposes. So we're gonna do a high pass filter. So we're just gonna filter out anything below 0.5 hertz so that I can let you look at what that's gonna look like. And it'll take a few minutes. This is a big file, so it's gonna take a few minutes to filter this data. I'm gonna tell it to change its name to put an HP out here so that we know it was high pass filtered. And we won't say that. This figure here shows you the filter characteristics, and this is what the filter looks like. You can see here at 0.5 hertz we basically have a pretty square edge. If I go to the actual MATLAB screen itself, I should be able to pull up, for those of you who have knowledge of digital filtering, this is a 3300 point filter, meaning it's 3300 order. So the reason it has to be excuse me, such a high order is if we go back to, let's look at if we go back to the filter window, you see this is a very sharp edge. So it requires quite a high filter orders to do that. Okay, now I'm going to go back and let's plot this filtered data. So first, it's got my data set active here. I'm on high pass filtered data. Let's plot and look at what the effects of that were. Okay, now you can see it's starting to look more like a data set now. I'm actually able to see all 65 channels. What has happened is the filter has eliminated that crazy DC offset, and so now I can see all of my channels. I can come in and ask it to only display. We'll do 15 at a time so that you can really clearly see what they look like. Okay, and sometimes the beginning of your data set is a little skewed because a lot of times you've got the instrument is sort of setting itself and you've got some stuff going on. So we'll go ahead and skip over to about the 8th or 9th second. Okay, now you can see there really is a big sort of, movement here in the data. So it looks pretty uniform, and then all of a sudden something goes haywire and you get quite a bit of noise, what looks like noise, and it's time localized. Okay. And here's another one. What these are these are eye movements. Right? And the ones that look like inverted plateaus tend to be horizontal eye movements. The ones that look like this tend to be vertical eye movements. And as you notice, they're localized in time and they have a fairly identifiable shape, but they're not part of the EEG. They're superimposed on the EEG. So just paging through. Okay, this is more of maybe a facial movement. Maybe someone clenched their teeth. Maybe they slightly moved their head. The reason I know this is I've looked at thousands of these. Let's go ahead and page down and look at some more channels. Okay, if we look at this channel right here, you see this really regular spike. This is actually a heartbeat. So superimposed on the EEG, you're picking up the pulse here. So with some subjects, you see that. With other subjects, you don't see it. You never know exactly when it's going to show up. You can see certainly on this channel that's showing up. Okay, let's come down a little further. Okay, so these channels right here, this channel 34, 35, kind of this 34 through 39 range. Um, for whatever reason, I don't know if it's a flaw in the instrument or a flaw in the cap, but I often have this kind of noise. And if we were to do a notch filter at 60 hertz, you would find that this is 60 hertz noise. So this is that instrument picking up the 60 hertz noise in the room. If you look at this channel, you can see I appear to have both 60 hertz noise and a heartbeat superimposed on that channel. So unlike a lot of the data that you're creating in class and that the textbook author is having you create, you can see that when you actually start to look at a real biomedical data set, things get very, very messy. All right, in this instrument, the bottom 5 channels have a specific use and application, and they're not really quite related to EEG. So CZ here is located at the very top middle of the head, and because of its location, it's often used as a reference or a ground. So that's the purpose that CZ is serving here in this particular data set. 61 through 64 are 4 channels located near the eyes. There are some techniques that we will discuss later this semester that allow you, if you are monitoring eye movements, they identify that as a specific independent component of the signal and you can remove it. So unlike filtering, where you would be filtering across a frequency range, the eye movement artifacts are often removed another way. So how should it look? It should look something like this. This data in here, that's pretty good. Come up a little a little higher up. That's pretty good data right there. Here's your heartbeat, but you can see a lot of these channels, you're getting pretty good, pretty clear. Here's an eye movement, but this isn't bad. All right, now let's go. The EEG has frequencies that are physically significant that basically run between 0 and 50 hertz. Now we have already done a DC filter to filter out the low frequency stuff. And so what I want to do now is I want to do a low pass filter. Let's get rid of everything below 50, and that'll take care of a lot of, not all, but a lot of that 60 hertz noise that I see. So let's rename this as soon as it asks me. Let's add the LP so that we know this has also been low pass filtered. And then let me pull up the filter characteristic window. Here's the magnitude. You see right here at 50, we have a roll off. But you notice it's not infinitely sharp. This is magnitude in dB. So remember, 20 dB down is an order of magnitude. So if we come over here to roughly 60 hertz, we can see we're still going to pick up some 60 hertz noise. We're still going to pick that up. All right, so now let's plot that data. Oh, and now it's really looking better. Okay, it's looking much cleaner. I've gotten rid of a lot of that higher frequency stuff. Let me reduce the number of channels I'm displaying here. We'll display a few more. We'll display 25 channels at a time. This is all this is doing is this is just adjusting, what the screen actually shows me. So let's come back up here. These top few channels are located near the front of the brain. And once again, this person is at rest. Their eyes are supposed to be closed, but clearly, even though their eyes are closed, they're either opening their eyes and moving them around, or they're like moving their eyes while their eyes are closed, which doesn't make any sense. So this once again goes to the messiness of collection of actual biomedical data sets, is that you're dealing with human beings. So even though this person was told to keep their eyes closed and their face relaxed, and that way they're not blinking, clearly there's some eye movement going on here. So um, compliance of human beings with being the perfect experimental setup is not always what you would hope it would be. So as we page through here, you can see lots of vertical eye movements. This is probably, as I said, a blink or someone clenching their jaw. But you notice that that heartbeat artifact has been greatly reduced. It's not completely removed, but greatly reduced. You don't see that high frequency component of that heartbeat like we were seeing it before. A lot of this 60 hertz noise has been minimized or reduced. So the data set definitely looks cleaner, but it's still far from perfect. So as I said, this is just with a filter applied, just a very simple filter, and you can see we still have some problems. So we're going to take this data set and work with it throughout the semester, along with some others. This is just one that I happen to collect in my lab. A lot of times when you collect an EEG, you're trying to find out what different scenarios do to the brain waves. So it's always a good idea when you're doing that to collect a set of resting state, what we call resting state data first. And that's what this is. And it forms kind of a baseline. It tells us when this person is at rest and their eyes are closed and they're relaxed and they're not being cognitively taxed. They're just sitting in a dark room with no sound stimulation, no light stimulation, um, and sitting still. This is just getting kind of a baseline of their EEG. Then we'll ask them to do things like answer questions or respond to sounds. or do something that requires that they are cognitively engaged, and we'll look at the difference. So that's kind of part of the clustering or pattern recognition part of what we do. But the signal processing part of what we do, basically, usually we will pre-process our data by doing some filtering, and then we'll begin our work because filtering is pretty fundamental. I mean, you saw I have some off-the-shelf software here that does a pretty good job. We'll begin our work then with a data file that looks like this. So trying to figure out what to do, what are we looking for. There are people who build careers off of automatically identifying these artifacts. So they'll come into to a filtered set of data like this and locate these, and you notice they're time localized. So this brings in a point about the stationarity of the data. When we do a frequency-based analysis of a data set, we're making an assumption that the data are fairly stationary. So if you're not from an electrical engineering background, stationarity of the data means that the spectral characteristics over time will not change. In this case, clearly, you have some time localized events that if we were to capture a Fourier spectrum here, power spectrum here, it might look quite different than if we captured it over here, say at 36 seconds. So the data are not stationary. What will happen are two things. First of all, if I'm looking for this kind of behavior and I do a frequency analysis, basically that frequency analysis integrates over time. So I'll lose any local events in the power spectrum because it'll average out. Secondly, if I have a lot of these, then the presence of these in themselves will be averaged into the power spectrum and it'll skew it slightly. So I'm looking at a power spectrum of not just an EEG, I'm looking at a power spectrum of an EEG with these eye movements or muscle twitches or heart rates or whatever's in this data averaged in. So, so that's the problem with a purely frequency domain analysis. But it's not bad. And so as you can see, just the simple filtering that we've done took us from, let me see if I can't find that original data. Okay, it took us from this to this, which removes the DC component, to this, which removes some of the higher frequency components. And yes, the software is auto scaling the display, so I am seeing some sort of skewing of that as far as what I'm actually seeing on the display window. But I think you can agree it's pretty dramatic the way just the simple filtering helped and got rid of some of the problems that were in the original two plots. So that just wanted to step you through this data. I'm going to make this available as a Excel file, and if I can do it, I'll try to get it also as a .mat file so that you then have the ability to go in and manipulate the data. And what we'll do as our first sort of mini project is look at some of what happens when you look at relevant frequency bands through using some bandpass filtering in an EEG signal.